Hello everyone. In today's lecture we shall consider the kinetics of elimination. So in the earlier lectures we have covered all the aspects of pharmacokinetics, that is absorption, distribution, protein binding, tissue storage, metabolism as well as excretion. Okay, now let us move on to the next point, that is kinetics of elimination. Okay, now kinetics, the term you all are already familiar with. Okay, so kinetics means movement. Okay, so exactly what is happening or what are the parameters for the elimination of a particular drug. Now let us see first of all what is drug elimination. Okay, the elimination, it considers both the metabolic inactivation as well as the excretion of the drug. Okay, so wherein the drug, it either it is removed out of the body so that it won't produce in any action, or its metabolic inactivation will take place, that is it will be converted to inactive metabolites which will not show any therapeutic effect. So metabolism, we have seen that there are actually three purposes of metabolism, right? So either inactivation will take place, that is your drug will get converted to inactive metabolite, it will get activated, that is it will get converted to an active metabolite, or an active metabolite will be generated from the active drug. Okay, so here that metabolism is considered which produces only inactivation, that is your drug is converted to something which will not show any therapeutic effect, or simply the removal of the drug from the body. So that will also eliminate your drug from the body. Okay, so actually here the drug is present in the form of metabolites which is not showing any therapeutic effect, but here the drug is totally removed out of the body. So considering these two processes together, it constitutes of the elimination of a drug. Okay, now one thing which should be kept in mind is elimination of any drug, it will take place only from the central compartment, that is from the blood. Blood is your central compartment. Okay, so initially your drug will enter into your systemic circulation. So for it to produce its action, it should go to blood. So blood will take it throughout the body. Maybe your site of action is present in some other compartment. So likewise, there are multiple compartments which are present in the body, so out of which blood is one, and blood acts as a central compartment. So actual elimination of your drug, it takes place only from the blood. So even if your drug is distributed into your tissues, say if it has entered some of your cells, so ultimately its elimination will take place only when it comes back to your blood. So blood will take it to the eliminating organs. In case of metabolism, maybe it will go to liver, or some other organs are also involved as we have seen, or if it is supposed to be excreted, it will be taken to the kidney by the blood. Okay, or maybe it will come out from the blood and it will move out of the body in the form of exhaled air, or it will go into the sweat or saliva, feces and so on. Okay, but blood is eliminated always from the central compartment, that is the blood. Now why do we need to study these kinetics of elimination of a particular drug? What is the purpose? Okay, so basically these kinetics of elimination, you need to know how exactly this elimination is taking place. What are the parameters which will govern? There should be some parameter which should measure this elimination of the drug. Like say for example, in case of absorption, we have seen that the parameter which determines the absorption is bioavailability, right? You measure the absorption of the drug in terms of bioavailability. How do you come to know that the drug is absorbed systemically? It's depicted from the bioavailability of that drug. Okay, in case of distribution, we have seen that the volume of distribution, apparent volume of distribution, so that will tell you exactly where the drug is distributed. So likewise, each aspect of pharmacokinetics, it has a particular parameter which measures that particular aspect of kinetics. So in the same way, taken together, this metabolic inactivation and excretion, it can be measured. You can have an idea how exactly at what rate it is eliminated from the body. That's very important. You just like you need to measure the absorption, how much amount is absorbed, at what rate it is absorbed. At the same time, you also need to know at what rate the drug is inactivated or at what rate it is removed out of the body. That is also very important. Okay, now why do you need to measure this elimination? Why kinetics of elimination needs to be studied? So first of all, that will provide the basis for your selection of the dosage regimen. Also, it will help you to design a rational dosage regimen. Now, what do you mean by rational? Rational in the sense it should be ethically correct. Okay, it should not happen that when some drug is not required, a treatment is not required, it should not happen that you forcefully give the treatment to a particular patient. Or say, supposing if one tablet serves the purpose to cure that particular condition or to treat that particular condition, you should not be giving 4 doses to that patient. So that is irrational prescribing. Okay, something which should be rational. Your dosage regimen which you are selecting, the way in which the drug is supposed to be consumed, it should be rational. So that will give you the basis to select the rational dosage regimen for a particular patient, depending upon the requirement, depending upon the condition, or depending upon that particular situation of the pathological condition, or maybe some other health issues. Okay. So also these kinetics of elimination will also help you to modify these regimens as per the individual needs. Say for example, elderly. In them you know that the kidney doesn't function properly, right? We have seen that kidneys, their function go on declining as the age progresses. So you need to individualize that particular dose, right? So you need to modify your dose or modify your regimen according to the need. Supposing if the patient is suffering from renal failure or hepatic failure, so accordingly you have to adjust the dosage regimen. So if you have the idea of the kinetics of elimination, you can very well adjust the dose according to the need of that particular patient. Okay. Now, while you consider a particular drug or the selection of a particular drug, there are 3 important pharmacokinetic parameters, okay, which needs to be known about a particular drug, okay, for you to know the kinetics. Okay. That is bioavailability, which is denoted by F, then volume of distribution denoted by B or V or VD, and the third one is the clearance, or it is denoted by CL. Okay. So these 3 needs to be studied in detail for any drug to know its pharmacokinetic profile. Now out of these 3, bioavailability we have already considered under the absorption. Okay. Then volume of distribution also we have already covered under the distribution. Now coming to the clearance, this is the parameter which actually deals with the elimination of a particular drug. Okay. Of course, it will be governed by even the volume of distribution and bioavailability also. All of these play an important role. Okay. So herein we are going to consider the third parameter, that is the clearance of a particular drug. Okay. So clearance, let us see what clearance means. Okay. So clearance of a particular drug, it is the theoretical volume of plasma from which the drug is completely removed in unit time. Okay. So per unit time, how much volume of plasma is totally cleared of your drug. That is, from that much volume of plasma, say 50 ml of your plasma, completely the drug will be removed out. Okay. So this is determined in terms of unit time. So you in unit time, how much volume of your plasma is totally freed from. That means there won't be at the end of this unit time, that is at the end of this 1 minute, this much amount of plasma will be free from, totally free from the drug. Okay. And this particular clearance is also known as creatinine clearance. Now does it make any sense, volume of plasma which is completely cleared of the drug? Okay. Now your plasma volume, now the blood volume is around about 6 liters, out of which around about 3 liters is your plasma. Now, is it practically possible that only 50 ml of your plasma is completely free of your drug? That is, the drug will be removed only from the 50 ml of plasma out of the 3 liters. Is it practically possible? No, because plasma is uniform. Your drug will be uniformly distributed throughout the plasma, right? So that's why the term theoretical is used over here. So it's just a theoretical value. Okay, practically it is not possible to remove an entire drug from only a particular volume of plasma. It's not possible. Okay, so it's just a theoretical volume, just like your apparent volume of distribution. Okay, so this is also a theoretical value. It's a theoretical volume of plasma from which totally the drug is removed in unit time. Now let us see how it can be calculated. So this is the formula for calculation of the clearance. So it can be given by rate of elimination divided by C. C over here is the plasma concentration of the drug. Okay, so at a particular time, what is the plasma concentration? Usually plasma concentration of a particular drug is determined in terms of micrograms per ml. Okay, so here this is your blood vessel, the one which is shown in the red color. So it indicates the plasma concentration, that is 10 micrograms per ml is the plasma concentration of this particular drug which is depicted over here. Okay, so how you can calculate the clearance? Clearance is calculated by rate of elimination divided by plasma concentration. So plasma concentration you can find out very easily, right? Okay, so that is determined in terms of micrograms per ml, so you know this value. Rate of elimination. Now rate of elimination meaning it is the sum total of elimination of the drug, that is the metabolic inactivation plus the excretion of the drug. So metabolic inactivation will take place in the metabolizing organs, right? Like your liver is a main organ, and apart from this, kidney, lungs, skin, intestine are the places where metabolism will take place, and the kidneys are involved in the excretion. Mainly it is excreted in the kidney is what we have seen. So taken together, the elimination of the drug, that is metabolic inactivation plus the excretion of the drug from all the organs of elimination taken together, how much is the rate of elimination, that is what amount of drug is removed per unit time. Okay, so in this case all the organs of elimination, they remove your drug at the rate of 500 microgram per minute. So in a unit time 500 micrograms are removed per minute. Okay, so that is the rate of elimination. So how you can calculate the clearance? Rate of elimination, that is 500 micrograms per minute divided by the plasma concentration, which is 10 micrograms per ml. So obviously when elimination of a particular drug takes place, obviously what will happen to the plasma concentration? It will go on declining, right? So once it passes through the organs of elimination, plasma concentration will be less than 10 micrograms per ml. Okay, so this is how you can calculate the clearance, rate of elimination divided by the plasma concentration. So it is 500 micrograms per minute divided by 10 micrograms per ml. So it comes out to be 50 micrograms will get cancelled, ml it will go into the numerator, and minutes it is per minute. So it will be 50 ml per minute. Okay, so it is clearance is 50 ml per minute, that is per unit time, that is per minute 50 ml. How much volume of plasma? It is 50 ml of plasma which is totally cleared of your drug, that is from 50 ml of your plasma completely the drug is removed. Okay, practically it is not possible that only from 50 ml of your plasma the drug will be entirely removed. So this is just a theoretical value. Okay, so this is to do with the clearance. Okay, now let us see what happens to your clearance depending upon the kinetics of elimination. Now what kinetics that particular elimination is following? whether it is an exponential kinetics or whether it is a linear kinetics. So you all must be aware of what are first order reactions, first order kinetics and the zero order kinetics. Okay, so in case of first order kinetics, what happens? It is exponential kinetics, meaning the rate of elimination, it will change as per the change in the plasma concentration. Okay, so rate of elimination in this particular case, it is directly proportional to the drug concentration. So this rate of elimination, it is proportional to the plasma concentration. So as you change the plasma concentration, the rate of elimination will change proportionately. It is directly proportional. Okay, that means what? In this case, as we have seen earlier, it was 50 ml per minute when the plasma concentration was 10 micrograms per ml. Okay, now supposing if I double the plasma concentration, take a case over here. If I double the plasma concentration, if I make it 20 micrograms per ml, so what has happened to your rate of elimination? When it was 10 micrograms per ml, rate of elimination was 500 micrograms per minute. But now what has happened? As I have doubled the plasma concentration, the rate of elimination is also doubled. Okay, so proportionately it has increased. If I decrease the plasma concentration to 5 microgram per ml, the rate of elimination will become 250 micrograms per ml. Why it is changing? Because it is following the first order kinetics or exponential kinetics, wherein your rate of elimination will be totally dependent upon the plasma concentration. So here what you can conclude, a constant fraction of your drug which is present in the body, that is eliminated in unit time. Okay, so out of the total amount of drug which is present in the body, a certain fraction, that is a certain percentage of your drug is getting removed out. It's not the constant amount, it is the constant fraction or a constant percentage of your drug is removed out from the body per unit time when the kinetics of elimination is following first order kinetics. Okay, so now next situation is where your kinetics, they follow the zero order kinetics or linear kinetics. Okay, so here what happens is the rate of elimination is constant. Supposing all these organs of elimination, these are already saturated, all the processes are saturated. Okay, so for 10 micrograms per ml of your drug, when this is the plasma concentration, the amount of drug which is getting eliminated, that will be constant. So the rate of elimination, it remains constant irrespective of the drug concentration. Okay, so whatever the drug concentration may be, it may be 10 microgram per ml, whether it will be 20 microgram per ml or 100 microgram per ml, the rate of elimination does not change over here. Okay, so rate of elimination, so in this case it was when the plasma concentration was 10 micrograms per ml, it was 500 micrograms per minute, right, the rate of elimination. Now when I double the plasma concentration, that is 20 micrograms per ml, if I make the plasma concentration, what has happened to your rate of elimination? Has it changed? No. In the previous case where first order kinetics was followed, it has doubled when the plasma concentration has doubled. But here in this case it is not changing, it is remaining constant. Okay, so it does not change with the change in plasma concentration. So in that case what will happen to your clearance? It will, as you increase the plasma concentration, the clearance will go on decreasing because your plasma concentration is in the denominator and numerator is remaining unchanged. So now supposing if I increase the plasma concentration from 10 microgram to 20 microgram, still rate of elimination will remain 500 micrograms per minute. So clearance will be 25 ml per minute. So it will half when you double the dose. So as you increase the dose, what is happening? As you increase the plasma concentration, the clearance will go on decreasing. Why it is decreasing? Because the rate of elimination is constant. So here what you can conclude from this, a constant amount of drug is eliminated in unit time. So whatever may be the amount of drug which is present in your body, this particular value, whatever is the amount, the rate of elimination will be the same. That is, every time only 500 micrograms of your drug will be removed out of the body. That is a constant amount. In the earlier case it was constant fraction, that is a particular percentage, but here a constant amount is getting eliminated from the body per unit time. Okay, now this particular situation, it is known as the capacity limited elimination, or it follows the Michaelis-Menten elimination. Okay. Now in certain cases of the drugs, the kinetics, it changes. Initially maybe it will follow the first order kinetics, that is, initially slowly when you increase the concentration, the rate of elimination may increase, but later on a time will come wherein all the elimination processes will get saturated. So excess amount of the metabolizing enzymes or the filtration rate, it will be saturated, right, so that it will remain constant. So initially it will be first order, but slowly as you go on increasing the plasma concentration, it will reach saturation and it will change to zero order. So further, if you increase the plasma concentration, it will start decreasing the clearance. Okay, so plasma concentration will increase disproportionately because your drug is not being removed out of the body. Only a constant amount will be removed out of the body. Then the next concept is plasma half-life, or the T half-life of a particular drug. Okay, now let us see what this plasma half-life, how it can be defined. So plasma half-life of a drug, it is the time taken for its plasma concentration to reduce to half of its original value. Now supposing initially if the plasma concentration was 100 micrograms per ml, so how long is taken for that plasma concentration to reduce to 50 micrograms per ml, that time which is required to drop its initial value to 50%, okay, half of the original value, that is known as the half-life of a particular drug. Okay, now let us consider this with the help of an example. Supposing if you are administering a particular drug, it gets distributed in one particular compartment, and it follows the first order elimination. Okay, first order elimination means it's as you change the plasma concentration, the rate of elimination will also change. Okay, and when it is given by IV route. So supposing if you administer that particular drug by IV routes, so when you do this, entire amount which you are administering, that is in your systemic circulation. So you know how much of your drug is in the plasma, right? So you know the plasma concentration. Whatever you have administered, entire thing is in your blood circulation. Okay. Now supposing after administering of that particular drug, you monitor the plasma concentration after a particular time interval. If you go on monitoring, now when I am administering that at say 10 AM, so after say 2 hours I am again checking what is the plasma concentration, say at 12 noon, after that at 2 PM, after that at 4 PM. So at regular intervals, if I go on monitoring what is the plasma concentration, and if I plot that, okay, on a graph, so I'll get a graph which will look something like this. Okay, so time I have plotted on x-axis and the plasma concentration on the y-axis. Okay, now here the time which is getting depicted, it is considering the time of administration as 0. Though I have administered it at 10 AM, so that particular time will be considered as 0. So after 2 hours again I have checked what is the plasma concentration. Okay, so after 2 hours, say it is around about say 16. Okay, so after 4 hours again I have measured the plasma concentration, and I have found that it is 8 micrograms per ml, and so on. After every 2 hours interval, I have measured what is the plasma concentration, and that I have plotted on the y-axis. So I'll get a particular curve. When I join all these points, I will get a particular curve, right? Okay. Now this particular line, if you can see, it has two slopes, right? So initially when I have administered a drug by IV route. So I know that whatever I have administered, entire thing is in your systemic circulation. So what amount I have administered? 64 micrograms per ml was the dose of drug which I have administered to that particular person. Okay. Now as the time elapses, what has happened to your plasma concentration? It is going on reducing, right? Now why it is getting reduced is because once your drug is in your systemic circulation, will it remain in your blood? No, your blood will carry it throughout the body. So it may get distributed, right, throughout your body. It will enter into your tissues, your body fluids, other body fluids, they will take up your drug, right? So your drug will get distributed initially, and after some time, a time will come wherein the drug will start getting eliminated. Okay, that means it will either get excreted out of the body, or it will get converted into inactive metabolites. So metabolic inactivation will take place. So that's how there is initially sharp decline in concentration. Why there is sharp decline? That's because of the distribution. Rapidly the drug will get distributed to other tissues. Okay, so if you consider this line, it has two slopes, right? The first one, that's alpha, that's denoted by alpha over here. That's because of the initial rapid declining phase. That's due to the distribution. And the later part, it has a different slope, that is denoted as beta. Okay, so this is less declining, if you can see. Okay, this particular slope. So this is basically due to the elimination of your drug. So initially there will be a rapid decline, later on there will be a slow decline in the plasma concentration. Okay, now as you can see, what is happening over here? Now initially it was 64, after some time it has declined to 32. So its plasma concentration is reduced to half, right? Okay, from here again, if you go this way, okay, so after 2 hours of your administration of the drug, your plasma concentration has come down to 16 micrograms per ml. Further, from 2 hours to 4 hours, how much decrease in the plasma concentration has taken place? It has decreased from 16 to 8. Okay. Further, in next to 2 hours, what has happened? The plasma concentration at 4 hours, it was 8 micrograms per ml, but at 6 hours, it has become 4 micrograms per ml. So what is happening? The concentration of your drug is reducing to half of its original, right? From 8, it has come down to 4. Then again, from 6 hours to 8 hours. After 8 hours, what has happened? From 4, it has come down to 2 micrograms per ml. So again, it has half. Okay. From 8 to 10, if you can see that the plasma concentration has again half. From 2, it has become 1. Okay. So what you can depict from this is these 2 hours interval is the T half-life of that particular drug. Why? Because it is the time taken to reduce the plasma concentration to half of its original value. So at 6 hours it was 4 microgram per ml, but at 8 hours it has become 2 microgram per ml. So it has reduced to half. So you can depict from this that the T half-life of the particular drug is 2 hours. Okay. So as I have told earlier that there are two slopes. There can be 2 T half-lives which can be calculated, but the initial one is due to the distribution. So we are interested in the later one, that is the elimination T half-life of that particular drug. Okay, so the formula which is given to calculate the T half-life of a particular drug, it is ln2 divided by k. ln2, it is a natural logarithm of 2, the value of which is 0.693, and k is the elimination rate constant of that particular drug. That is how much fraction of the total amount of drug it is removed out from the body per unit time. Okay, so what this formula will turn out to be, T half life is equal to, when you replace this value by 0.693, it will be T half life equal to 0.693 divided by K. This will be your formula. Now how can you find out the value of K, okay, or the elimination rate constant? Okay, now supposing if the total amount of your drug present in the body is 2 grams, and say every hour out of this 2 grams 0.1 gram is removed out, or it is eliminated. Okay, either inactivation will take place or excretion will take place. So how you can calculate K? The amount which is eliminated every hour divided by the total amount, that will give you the elimination rate constant. So in this case it will be 0.05, or it will be 5% per hour. So this is how the elimination rate constant can be calculated for a particular drug. Now this elimination rate constant, it can be calculated from these parameters, that is clearance divided by volume of distribution. These can be known, right? It can be found out, the clearance and the volume of distribution. So by substituting these values for K in your formula, the formula for T half life, as we have seen, it was 0.693 divided by K, right? So when you substitute the value of that K in the denominator, the formula it will become T half life equal to 0.693 multiplied by V. This will go in the numerator and Cl will remain in the denominator. So this is the formula for your T half life. Okay, so this is how the T half life of a particular drug can be calculated. So T half life of a drug, it is dependent upon the volume of distribution and the clearance of that particular drug. Okay, however, as such these two parameters, okay, they may change independently. So as such the half life of a particular drug, it will only give you a rough value. It will not give you an exact value. But anyhow, you can use this particular parameter to find out how much time will be required for complete elimination of that particular drug. You can find out that approximately how long it will take for your drug to be removed out of the body. Like say for example, after the first T half life. What is T half life? T half life is the time required to reduce the concentration of your drug to half of its original value. So that means what? After first half life, 50% of your drug is eliminated from the body. Okay, so how much is remained in the body? Remaining is the 50%. It's already there in your body, and 50% is eliminated out of the body. Okay, now what will happen? After that, the second T half life will start. Now whatever 50% is remaining in your body, out of that, in the next T half life, out of that 50% of the drug will be removed. Okay, so what will be the total elimination after 2 half life? Already after first half life, 50% of the drug has been removed, and after the second half life, 50% of the remaining 50% has been removed, that is 25%. So total after second T half life, 75% of your drug has been eliminated out of the body. Now once 75% has been removed, what is the remaining amount of drug in your body? It's 25%, which is left in your body, right? So out of that 25%, again half of it will be removed in the next T half life. So after third T half life, what will be the amount which is removed? Initially in the first T half life, we have seen that 50% is removed. In the second T half life, additional 25% is removed, and in the third T half life, half of 25, that is 12.5 has been removed. So total 87.5% of your drug is removed after the third T half life. Okay, say for example, T half life is 2 hours. Then after 2 hours, 50% drug will be removed. After 4 hours, 75% of the drug will be removed. After say 6 hours, 87.5 will be removed, and after 8 hours, 93.75. How you have come to this? Initially 50 plus 25 plus 12.5. So what is the remaining amount in your body? It is 12.5. So out of that, half will be removed, that is 6.25. Okay, so that's how this value is 93.75%. Okay, so what you can conclude is nearly about 4 to 5 half-life time is required for your drug to completely get eliminated from the body. However, this is only a predicted value. Exactly it won't be the same practically. Okay, but you can depict exactly how long or roughly how long a particular drug will take to be removed out of the body. Okay, now this T half-life, again it will vary depending upon the kinetics of the processes, right? Now supposing if first order kinetics is followed by that particular reactions for the elimination or the processes of elimination, if they follow the first order kinetics. So what we have seen over there, that in case of clearance, what we have seen, that V and Cl, the clearance, it does not change, right, in the first order kinetics. The rate of elimination, it is directly proportional to the plasma concentration. So as plasma concentration is changing, the rate of elimination is also changing. The Cl does not change, it remains constant. V also does not change. So because of this, we have seen under the formula of your T half-life 0.693 multiplied by V divided by Cl. Okay, so since both the parameters have remained constant, T half-life also will remain constant. Okay, so this is the case with the first order kinetics. Now in case if the kinetics follow the zero order, okay, zero order kinetics, if it follows, then in that case the T half-life will increase. Okay, in that case the T half-life will increase. Now why it is increasing? Because under zero order kinetics we have seen that as the plasma concentration changes, okay, as you increase the plasma concentration, the Cl decreases, right? Okay, as you increase the dose, the clearance goes on decreasing. Now since clearance in the formula of T half-life, the clearance is in the denominator. So because of that, the T half-life will go on increasing if your drug is following the zero order kinetics. Okay, so T half-life will be again dependent upon the kinetics of the elimination. Now these are some of the examples of the T half-lives of the drugs. So it is totally a characteristic feature of that particular drug. Okay, aspirin, it has 4 hours of T half-life. That is 4 hours are required to reduce the concentration of aspirin to half of its original value. For penicillin G, it is just 30 minutes. Digoxin, it is 40 hours. And phenobarbital, it is quite long. 90 hours are required to eliminate just half of the drug from the body. Okay, so T half-life is variable for different drugs. Now, next concept under the kinetics of elimination which we can consider is the repeated drug administration. Okay, so as we have seen earlier that the kinetics of elimination will help you to better choose the regimen. Supposing if you want to repeat a particular dose of a particular drug, it's hardly any condition wherein you have to just take single dose of a particular drug. You may have to take multiple doses of a particular drug, right? So now how it should be repeated, how many tablets or how many doses are supposed to be given in a day. So how do you decide that? Okay, so that also can be depicted from the kinetics of elimination. So again it will be able to find out from the clearance. Okay, now supposing if you repeat a particular drug at short intervals, now you know that the T half-life of a particular drug is say 2 hours. Okay, so you know that after say 6 to 8 hours the drug will be completely removed out of the body. Now before the total drug is removed out of the body, if you repeat the dose, say after 2 hours itself you repeat the second dose of that particular dose. So what will happen? The drug will start accumulating in the body, because after 2 hours only 50% of the drug is removed, right? Still 50% is there in your body and you have added the second dose. So what will happen? Obviously the plasma concentration will be higher. Okay, so a time will come, as you go on repeating, a time will come wherein your administration will be balanced by the elimination and a steady state plasma concentration will be achieved. Your plasma concentration initially will go on increasing and a time will come wherein it will be balanced with the elimination. So it will reach a steady state plasma concentration. So it will remain constant, the plasma concentration of that particular drug. So how we can find out that steady state plasma concentration? It can be found out by the formula dose rate divided by the clearance. Okay, so from this what you can conclude is, doubling the dose rate, it would double the average CPSS. The steady state plasma concentration will double, it will increase if you double the dose rate. Okay, supposing if you are giving 2 tablets per day, if you give 4 tablets per day, obviously the plasma concentration also will be doubled. Okay, on the other hand, you can even work out the dose rate which is required. Now if you know what is the plasma concentration at which a particular drug shows the therapeutic effect. Now supposing if you know that therapeutic plasma concentration and clearance, obviously it can be calculated for a particular drug. So when you know both of these, obviously you can select an appropriate dosage rate for that particular drug. Okay, so dose rate for a particular drug can be target CPSS, that is you want this particular plasma concentration, say 50 microgram per ml is your target CPSS. You know the clearance of that particular drug. Okay, so when you multiply both these values, you will get the dose rate. What should be the dose rate? At what rate you are supposed to administer that drug to the particular patient. Now this is true for the IV administration, wherein entire amount of your drug is in your systemic circulation. But what about the routes of administrations like oral route? Here 100% of your drug will not reach your systemic circulation, right? Only a fraction of whatever is administered, bioavailable dose, right? Bioavailability should be taken into consideration, because entire amount will not reach your systemic circulation. Okay, so in that case you need to divide the target CPSS multiplied by CL by F, because entire amount will not be in your systemic circulation. So that's how you can find out the dose rate for an orally administered drug. Okay. However, for the drugs like phenytoin, which follow the saturation kinetics, wherein the kinetics changes from first order to zero order. Okay, so here what will happen, if you increase the dose rate, there will be disproportionate increase in the steady state plasma concentrations, right? So in that case you should be very careful while repeating the dosage, which should be adjusted, because the rate of elimination over here, it is depicted by this particular formula, Vmax multiplied by C divided by Km plus C. C is the plasma concentration, Vmax over here is the maximum rate of drug elimination, and Km is the plasma concentration at which the elimination rate is half of the maximal value. Okay, so this is how the graph will look like in case of first order kinetics. As you increase the dose rate, there will be proportionate increase in the CPSS, the steady state plasma concentration. But in case of zero order, okay, so what will happen? A time will come wherein saturation will take place, and if you increase the dose rate, there will be disproportionate increase in the plasma concentration. Okay, so that will increase very steeply. So you should be careful while administering such drugs which are following zero order kinetics. Then the next concept is the plateau principle. Okay, now plateau principle meaning wherein you are doing repeated administration. Okay, now you know that a particular drug is eliminated completely from the body after say 4 T half-lives. Now supposing if you administer the drug before that particular drug is entirely removed from the body, say after first T half-life, if you add the second dose, obviously there will be increase in the plasma concentration, right? Okay, so as you go on adding the doses, okay, it will reach up to a particular level, okay, and it will balance itself at a particular concentration. When the rate of administration balances the rate of elimination, it will the plasma concentration will fluctuate around certain range. Okay, you can say that it will maintain itself in a constant range. Okay, now this particular way in which the plasma concentration is changing, that is known as the plateau principle. Now the figure will make it more clearer. Okay, so as the time elapses, when you administer the first dose, the concentration was 0. Okay, so slowly it will increase, plasma concentration is increased, but the time will come wherein it will start getting eliminated out of the body. So slowly the drug will be eliminated. Okay, so this curve also we have seen under the bioavailability, right? So slowly it will eliminate, it will be removed out of the body. But supposing if you administer the second dose at this particular time, wherein entire drug is not removed, only the 50% of the drug is removed. If you add the second dose, obviously the plasma concentration will increase. Slowly it will start declining, but again if you give another dose, it will again further increase. So if you continue this, say round about after 4 to 5 T half-lives, your plasma concentration of your drug will start fluctuating in a particular range, a particular maximum level and a particular minimum level. Okay, so that particular concept is known as a plateau principle. That will be when you administer the drug repeatedly, it will initially increase and then later on it will stabilize. Okay, so it will get a shape of a plateau. That's why it is known as a plateau principle. Okay, so this fluctuation in the plasma concentrations which is done, ideally a fluctuation of a plasma concentration is not acceptable. Okay, average CPSS, you can say that it is at this 1/3 of the level of this fluctuation. Okay, so ideally the fluctuations are not advisable, but you can minimize these fluctuations by selecting appropriate intervals after which you are adding the new doses. Okay, however, if you change the dose rate, automatically the CPSS, that plateau which occurs, that will also adjust accordingly. Okay, it will change. And the next concept is target level strategy. Okay, now supposing if there is a drug which cannot be easily quantified, or the safety margin of the drug is if the safety margin of the drug is not very large, like say anticonvulsant, theophylline, lithium, antidepressants and so on. So in this case you just can't administer a certain amount of drug to reach, or you cannot wait for your drug to reach the steady state plasma concentration. As we have seen that say 4 to 5 repeated doses are required for your drug to reach the steady state plasma concentration, right? So there are certain situations wherein you cannot wait up to that much of time, right? Okay, so what you can do is, in this case you can have a target level strategy, that how much of plasma concentration is required. Like fluctuations, as I have told you, it will take place. In certain cases fluctuations may not be advisable. Okay, but in situations wherein the drug with which are having shorter T half-life, it can be administered at certain conventional intervals, so that the fluctuations in the plasma concentration, these are not marked. Okay, so administration or the range or the interval after which the administration is supposed to be done, that has to be carefully chosen depending upon the type of drug. In case of the drugs which are having long T half-life, if you go on adding the dose, what will happen? It will start accumulating and toxicity will be taken place. Okay, so that is also not advisable. Okay, delay is also not advisable. So how you can tackle all these situations is that you can administer the drug in 2 doses, an initial loading dose and subsequent maintenance dose. Now let us see what is the loading dose. So initially what you can do is, to achieve a particular plasma concentration, you can initially give a single high dose or few quickly repeated doses, small doses which are repeated quickly at shorter intervals. so that you will quickly attain the target concentration. So loading dose, how you can calculate? Target Cp, what is the plasma concentration which you require, multiplied by the volume of distribution divided by the bioavailable fraction or bioavailability of that particular drug. Okay, so here loading dose, if you can see, it is governed by the volume of distribution and not by the clearance or T half life of that particular drug. Whereas maintenance dose, this is the dose which is to be repeated at specified intervals after the attainment of the target CPS. So once you have reached that CPSS, now you know that you have reached the required plasma concentration. So you need to maintain that plasma concentration within that particular range after balancing with the elimination. So in that case, the maintenance dose, how you can calculate it? It's the same formula as that for the dose rate, that is target CPSS multiplied by clearance divided by bioavailability. Okay, so it is governed by the clearance over here or the T half life of the drug. Thank you.